Okay, so if you go into Canvas, like I said, get assignment 1 in for me. But I've gone ahead and published these things that are green. These are published. You can see those on your screen. If you have any access issues, if you click on something and it says access denied, let me know. Sometimes there's about 5 places I have to publish something before you can actually see it, depending on how it's set up. So if something, if you think you should have access to something and you click on it, it says no, then just send me an email and let me know. I'm getting a lot better at not having those little things. But anyway, when you go to modules, we get the module for course materials here, and there's some new stuff is green for you. You got access to. Let's talk about what we want to talk about today is a little bit about the history of engineering and how we got here and where we're at. This is not a history class by any means. I'm not a history expert by any means, but over the years I've learned a little more about the history of engineering and how we got here, and there's some really important, really cool stuff goes on. And I don't know, if you're like me, it's like, Steve, I don't think history is very interesting. This sounds very boring. That's okay, I promise. I feel like for most engineers I've done okay trying to make this somewhat interesting. Let's start here. As we said, it's Intro to Engineering. One of our goals is to make sure you've got a really good, firm grasp on what is engineering. So let's start there. What is engineering? What do you guys think is engineering? What do you know of engineering, or examples? Or yes, sir?
Making everyday things easier and more efficient.
I like it. Everyday things easier and more efficient. That's a good start. Anybody want to add to that? A different take on it?
I would say taking things that this world provides, or even not this world, but and taking it and building things with it.
Okay. Taking and building things. Okay. Anybody else want to add to it? These are good. This is a good start. Yes.
Understanding how complex systems work and how to maintain and fix them.
Yes. Understanding and maintaining complex systems. Anybody else? Yeah.
Solving problems.
Oh, man. After my own heart. Everything here is fair for what engineers do. The truth is, it's really tough to put what we do in a black box, because it would take a really big black box. Solving problems is a huge component of it. Everything else that we've just put on the board there is a component of it. I don't know if this is the current definition on dictionary.com. I've not checked it recently. If you just go into your favorite search engine, I use Google a lot. I'm not getting paid to say that, so take that for what it's worth. I Google things a lot, and if you Google engineering definition or define engineering and see what comes back, you're going to get a lot of various definitions, but there's going to be some common themes show up in there, and you guys have hit on a lot of components of these. Just about every definition of engineering is going to have 2 main components. Right. Here they're saying it's the science or making practical application of knowledge of pure sciences in the construction of engines, bridges, buildings, mines, ships, chemical plants. One thing I wish this did say was solving problems. If I'm to define engineering myself, I would suggest it is, most importantly, it is the application of existing knowledge. That would be science, math, etc. To solve practical problems. Solving problems is a huge component of engineering. It's not the only component. It's one of the most important components. It's also the application of existing knowledge, the knowledge that exists out there, and trying to make practical use of it. Okay? So, if you think about and you understand, if I'm some sort of a researcher, so if I'm a professor at a large research university, right, for us that would be like OU and OSU, or just about anywhere else that they've got a large research facility. Those faculty members, those professors, it is typically their job to do research, to generate new knowledge, and also teach other people how to do research and how to generate new knowledge. Okay? That is their primary goal, is research. Generation of new knowledge. So you have your scientists, your mathematicians, your physicists, your chemists, your biologists, etc. Their goal is to learn new things about the universe. It doesn't necessarily have to be practical. It doesn't have to be useful right now. There doesn't have to be anything that we're going to profit off of. Their goal is simply to learn new things. All right? And that information may sit on the shelf for centuries, millennia before it's used. All right? The mathematics that we use to encrypt data sat on a shelf collecting cobwebs for a long time because we didn't have anything. The computations, the calculations required to use that mathematics, it was to do it by hand was so intensive it just wasn't practical to use. Now we have computers that can do it quickly, right? And so the mathematics associated with that, like I said, just went untouched for millennia until finally we came along and said, here we've got a practical application where we need this information and we can apply that. Okay, so again, if you kind of have different occupations, you've got your researchers, your scientists, whose sole job is to generate knowledge. The engineers, our job is to take the knowledge that exists out there and try to put it to work to solve problems that exist now. Okay, and then the next level, you're going to have people that are we sometimes refer to technicians or technologists, whose goal and job a lot of times is to try to take the designs that the engineers come up with and try to figure out what's the best way to build that or create that or actually do that. There's a lot of crossover there. There's a lot of engineers that do research and generate new knowledge. There's a lot of technologists that do engineering design work. There's a lot of engineers that actually do the building and the manufacturing sometimes. It just depends on where you go to work. Like I said, I'm careful and skeptical about trying to put engineering in just one box and draw a line around it and say, this is all of engineering, because it's much bigger than that, okay? But this gets you pretty close, and you guys hit on quite a bit of it. Designing new things, making things more efficient, more effective, maybe things that already exist. So sometimes it's creating new things, sometimes it's improving existing things, and if you look throughout history, you see individuals that have been doing this. I mean, arguably this is what humans do, right? Is exactly what I'm describing. Yes, but engineers take it to a different level, and we're formally trained in this art and this philosophy. But again, we can point to people throughout history that have done this, or things like it. And some of these names you probably know, some you don't. Most of us probably know Da Vinci, Imhotep. There's who knows who's Imhotep? Who knows who Imhotep was?
Pharaoh?
Wasn't actually a pharaoh. He was Egyptian though. Right? He's actually one of the few Egyptians that wasn't a pharaoh that we actually know his name. Like, he's actually famous. One of the few ancient Egyptians that we actually is recorded who this individual was. he was a priest and they call him a doctor, but he's also credited as the designer and the overseer of the construction of the first step pyramid. Right, so in the first step pyramid then was the basis of the iconic pyramids we think of today. It was kind of the first major pyramid that was built. Imhotep is credited as the first civil engineer who oversaw the construction of that structure. Mentioned Archimedes. Like I said, Leonardo da Vinci, probably don't have to say much about him. We got a nice little link here to just a Wikipedia. Is that going to fire for us? It's not going to fire for us. Come on now. Microsoft says, hey, there's security issues. I don't want to open this, doesn't it? There we go. All right. So actually, it just didn't come in. So Archimedes is credited with creation of various solutions. This is a nice little GIF image of what we call the Archimedes screw. You may recognize this if you've ever moved grain or some kind of granular material. You may recognize this as an auger. Boat propellers look much like this, just small, little slices of it. The idea is that if you hook up something that causes this rotation, and screws basically work the same way. You're just going to continuously feed material through that as you rotate it. It allows the conveyance or the movement of granular or liquid material pretty easily. The legend goes that Archimedes had been contracted, if you will, and today we'd call it contracting. He had been charged with trying to figure out a way to remove what we call the bilge, the liquid that accumulates in the bottom of a boat hull. Okay, and so back in this time, they didn't have solid cast aluminum hulls where there was no way for liquid to seep in. They had pieces of wood put together and smear tar in the gaps and tried really hard to keep the water out. As the vessels got larger and larger, there was just more places that water would come in, and if you didn't get that water out, the vessel's going to sink. So the solution at the time was they would just have an army of slaves that would basically bail water out, just pass buckets from the hull of the boat out and throw that overboard. What the legend goes is that Archimedes was charged with trying to find a better solution to that. The Syrian vessels had gotten so large that they couldn't, or it just wasn't feasible to keep that many slaves on board and manage them. So what they chose to do, or what Archimedes suggested, the legend says that this is one of the things he suggested, and they were able to implement. This will, if you design it correctly and adequately seal around the edges and spin it fast enough, this will actually move water from one location to another. Okay. All right. Thomas Savory. Anybody know who Thomas Savory is? Occasionally I'll have somebody knows who Imhotep is. Very rarely do I have anybody that knows who Thomas Savory is. Thomas Savory is credited as one of the first individuals granted a patent for a steam engine, any kind of a steam engine type of device. He had created some kind of device where he worked for a mining company and kind of the similar situation that Archimedes was dealing with. The mine shaft would fill up with water overnight or during idle periods, and so before the workers could get in there and actually get to extracting whatever they're working on, they would have to bail the water out. They'd have to mechanically or physically move the water out of their way. Savory created a device that, as best I understand it, as you heat a substance like water up, it wants to expand. Okay. Well, if I understand Savory's device correctly, basically that he was able to harness that expansion as you heat steam or water up and it expands. He was able to use that expansion to basically cause suction on another part. right? So, if you decrease the volume here, the volume has to increase somewhere else, and that was basically what he did and designed. It was some kind of a suction device that was able to kind of suck the water out of the mine shaft by expanding in another place. Okay, it's not the traditional, typical steam engine that we think about today, but it was one of the first applications of using heat to do mechanical work. So, again, this term engineering doesn't really show up, and it's not, the people that built the pyramids, they didn't call Imhotep an engineer, right? That term doesn't show up until later, but engineering work has occurred throughout the century, throughout the millennia. If you get an opportunity to visit some of the great wonders that still exist, or some of the, if you can get to go to Europe or somewhere in the Middle East and visit some of the large temples and shrines, it's really cool to see what humans were capable of and have been capable of over the years. And imagine that there's no computers or anything like that doing this. They're doing estimations at best, and if they are doing calculations, they're doing them completely by hand. So it's just really kind of neat to look back and say, all right, what all this engineering, if you will, that we've done. Great achievements to come. All right, hopefully we figure out this the rapidly growing population issue about we have an infinitely growing population and only a finite amount of space within which to house them and grow food to feed them, and that's we've solved a lot of it. I mean, we figured out how to grow crops very efficiently, and we've mechanized and automated a lot of agriculture. So we're meeting this challenge, but it's continuing to grow larger and larger. And honestly, we're meeting this alternative energy. It's now economically feasible in this current market to use solar and or wind as opposed to coal, for example. Right now, the price break is there, and the market is moving that way. So that's actually kind of interesting, and that's going to be interesting to see how that progresses over the next couple of decades. We're planning missions to Mars, right? Medical advancements. I mean, we are the hope is we're approaching a point where we can actually control this virus that we didn't even know existed 6 months ago. Well, places knew it existed. We some of us didn't know it existed. And we're approaching a point where we've got potentially a vaccine is possibly on the horizon. That took decades or centuries, but here we are now where it's feasible that experts are saying it's feasible that we could have a vaccine by the end of the year. That's crazy. Right? It's absolutely a testament to what we've been able to do. And let's talk about the reasons why we've been able to do that. Now, again, we're focusing on what is engineering and what is the history. Where do we come from? Well, where did the term engineer actually originate? The term engineer, again, I'm not claiming to be a history expert, and I've not looked at the original text where the term initially showed up. I've not gone to that extent. Just kind of a casual dive. The term engine apostrophe most sources agree this term began to show up in the English language somewhere around the 14th century. And somewhere around the 14th century, about the 1300s, this term began showing up in texts, referring specifically to those who constructed and operated siege engines, military siege engines, catapults, trebuchets, ballistas, things of this nature. Now, this is not the modern iteration of engines that we think of, but these were kind of like engines. They are devices that convert one type of energy to another. Right? So engines today do convert one type of energy to another, and that's the reason this definition does pass muster here. But this is where the term originally began to appear, as not there are definitely engineers that build catapults and trebuchets for fun today, sometimes competitions, but that's not necessarily what we do today. Okay, I don't know. I guess there probably are some that do this seriously, but soon. That's initially kind of the initial engineers. That's where they showed up. Soon after that, we started dividing them into two major groups. You have your civil engineers that build solutions to problems associated with civilization, right? And you've got your military engineers building devices for military purposes. And sometimes they were the same individual. It's just when we went to war, your civil engineers became military engineers and vice versa. So, but the two oldest fields of engineering we typically point to are civil and military engineers as the two oldest fields of engineering. Military engineering doesn't necessarily exist. It does exist today, but it tends to be kind of divided up into various subsections, more modern subgroups of engineering: mechanical, electrical, aerospace, industrial, and civil sometimes. Right? So we don't necessarily call engineers military engineers today, but there are definitely still, civil engineering is still a large field of engineering. Okay. Man. Normally I ask this, but that's okay. Let's talk about, if you think about, we've talked about the really interesting, amazing things humans have done over the past several millennia. And we say, hey, well, why did it take us this long to get where we are now? Right? I mean, that's millennia, that's centuries ago that we built the pyramids. Why did it take so long now to be able to do anything close to that? Or there are records that suggest the existence of what's called the Baghdad Battery. Right? So that's talking about in ancient times that people were aware that chemical reactions could cause an electrical current. Now, they didn't call it electricity, but there's archaeological evidence that people were using acidic solutions and anodes and cathodes and it's unclear what they were doing with them, but all structures very obvious are battery structures that existed. So where did that knowledge go? Somebody knew what they were doing with that. Why then does it take a millennia before modern batteries appear? Well, here's a few factors that we can point to and say this is kind of what really slowed the work of early engineers and even those individuals that we didn't call engineers like Da Vinci or Archimedes. Slow communication of ideas, first and foremost. Slow communication of ideas. And this is hard. Sometimes it's hard for us to fathom that what we know right now can be known in Japan, Russia, and China in seconds or less. Okay, that's modern. That's new, and being able to communicate in a way that they understand it. Now, the second one here, what I would suggest is of these four, three of these we've basically completely defeated. Right? We have all but removed these, and the second one here is we've done some things. We've learned as a world how to mitigate this second one some. After the world wars, we learned about how can we try to cut off this fear of technology being used against us and work together to mitigate that. I think we're forgetting some of the lessons we learned during that time period, but hopefully we start remembering those. But let's talk about the other three first. So like I said, slow communication of ideas, we've completely eradicated that one for the most part. Lack of standardized methods. What is this? It's not a yardstick, actually. This is a meter stick. This is a meter stick. Everybody in the world knows what a meter is. Americans have an idea. Right? That's French for, foot, isn't it? No, it's a meter. It's, for us, it's about 39 inches, a little more than 39 inches. So a little longer than a yardstick. Yardstick's 36 inches, so the yardstick stops here, okay? No, this is a meter, and that's a standardized quantity that everybody in the world knows what that is and what that represents. That's a standardized method. There's the legend, and I believe I call it a legend. I'm calling it a legend because I've not gone through and really dug out the facts and looked at it, but the legend goes that a firearms manufacturer, I believe it was Browning, was able to win a contract with the U.S. government by creating standardized parts for his firearms. And he was basically able to say to some lawmakers, either some congressmen or some senators, and say, all right, I want you to pull one part from each of these 5 bins. And he took all the parts and put them together and was able to fire. Put them together into a pistol and was able to fire it. Up to that point, every time, what he found, the legend goes that, somebody would come in and their trigger would be broken on their gun that they had bought from him, and they'd say, I need a new trigger for my gun. I broke it. And what he would have to do is every gun was slightly different, so every time he was having to build a unique trigger to fit that particular gun, and he got tired of it. He realized it's just a trigger. It does the same thing. Can't I just make the same trigger over and over again, and that works for every gun that I make? And that's set off then a chain reaction of, okay, well, I don't have to make the trigger. I've got this apprentice over here. I can teach him how to make the triggers, and I can teach this other apprentice how to make the flintlocks, and I can teach this. And so you start breaking it down and standardizing the components. And just like everybody knows what a meter is, and so if you've got the same component that you standardized, that speeds up, and as you can communicate that more quickly, as we solve problems and as knowledge exists, then we can be able to use that to solve practical problems more rapidly. Day-to-day tasks, the 4th one here, let's talk about that. Other day-to-day tasks. Imagine, could you guys be here right now in a college classroom if you had to worry about how are you going to feed your family through the winter? You're out in the field harvesting because you got to store enough food to get you and your family through the winter. Imagine doing what you're doing right now. That's crazy. I can't do that. No, I got to go to work. I got to feed the family. Day-to-day tasks. So the idea one way we've solved that is simply by the creation of currency, right? So we have this pretend make-believe substance called the dollar that we can trade, right? And so I can get really good at what I do, at least try to, I hope I am. You can focus on what it is you want to get really good at, and you get to a point where that's something that you can exchange, this made-up quantity that we can exchange with one another for our time, or our efforts, or our goods, right? And so I don't have to, imagine if you had to show up here to try to pay your tuition with chickens and bushels of grain, and we got to figure out what's the exchange rate, and everybody's going to be different. Somebody's going to bring in milk. No, we uniform this made-up quantity we call the dollar, which again I'm not trying to downplay it. I'm a big fan of currency because it solves this problem. Your other day-to-day tasks, you don't have to focus on growing enough food for yourself and your family. You can focus on things that you're interested in or have skills or abilities that lend themselves to doing other things, and you become specialized at those. And you allow people to become specialized and really, really good at what they do. And again, figure of technology being used against you. So when we create something new, and especially like with, for example, nuclear energy, we can still harness nuclear energy, but we do have this fear of it being used against us. And that's kind of the one that we've got pretty good systems in place. We've been trying to tackle that one, but it still does exist, and I don't know that we'll ever completely eradicate it. But the other 3, we've definitely eradicated, and the second one there, we've done what we can to mitigate it. Okay, so again, just kind of continuing on that theme, as cities began to grow, as people were able to kind of move away from a nomadic way of life, they were able to develop agriculture, they were able to settle, and so one farmer could feed more people, and then you had people became good at making tools, so the farmer became better because they had better tools, because somebody got better at making tools, and it just begins to kind of snowball and grow. Okay? So that's kind of how we get where we are now. Now, I want you to think about, and let's make a list here. What are some things that you enjoy today or use today or interact with today that didn't exist 300 years ago, 1700s?
Internet.
Internet. Absolutely. What else?
Air conditioning.
Yes, ma'am. I'm a big fan.
Door
HVAC.
lighting.
Lighting. That one normally takes a little while to show up, if it even shows up. I'm glad you said that. Lighting. Absolutely. Imagine if your day ended when the sun goes down. Somebody like me, I couldn't do it, man. It's crazy. Yes, ma'am.
Water heater.
Yes. I like that. Hot shower's good. What else?
Food processing.
Yeah. Food processing, is that what I heard?
Yeah.
Okay. Yes, I agree. I'm also a food engineer, so that's kind of near and dear to me.
Motor vehicles.
Yes, ma'am. Vehicles. What else? Yeah.
Modernized farming equipment.
Yes. Modern farm equipment. Absolutely.
Vaccines.
Vaccines, yes. We don't have to worry about getting polio or smallpox. That's kind of a big deal.
Clean water.
Clean water, yes. And that's something that does actually hold a lot of places back still in this world, unfortunately. That's a good list, guys. And we could keep going, right? We could definitely keep going, but I think that gets us started. One thing I always notice, nobody, and you guys got a lot closer than a lot of groups do, I would suggest probably all of these don't exist without one common
Electricity.
electricity. Electricity. We don't even think about it. And don't, seriously, guys, it's very rare. I've been teaching this class for 13 years and sometimes 2 sections a semester. I can only think about twice that anybody says electricity when I ask this question. Right? We just completely take that for granted. Okay? And again, that goes back to the modern lighting. Like I said, lighting gets us closer than we typically get there, and that's okay. But it's just interesting. Okay? So why did all this happen in the last 300 years? Well, again, because we start really knocking down those 4 factors we talked about: slow communication, fear of technology being used against you, day-to-day tasks, and standardized methods. We've really eradicated and really pushed back hard as a civilization against all 4 of those in the last 300 years. If we take a little strip here, 18th century, 1700s. So I believe Savory's patent is in the late 1600s. Early 1700s, we start seeing steam engines, the actual modern version of the steam engine where you've got a piston moving back and forth. That begins to appear in the early 1700s. In addition, we began to understand more about electricity. It's not just this magic quantity. I mean, it still is magic to most of us, right? But science begins to have a better understanding that magnetism causes electricity and electricity causes magnetism, and that there's an actual relationship between those two that we can quantify. And we learn about storing electricity. Traveling technologies continue to improve, right? So we know there's these Americas out there. We get better at getting there faster. And because the steam engine begins to show up, the Industrial Revolution commences. So a couple things. We mentioned Browning and the firearms and the standardized parts. That's one thing, right? So you can start having individuals focusing on just making certain components and getting really good at them, and then we start figuring out how to move those quickly. But I also don't have to build my textile mill or my flour mill next to a flowing stream so I can use a paddle wheel to get power to run my big machines. I can just go buy a steam engine, have it installed, and anywhere that I can feed that steam engine some kind of fuel source, I've got power ready to go. So you have larger facilities because there's more energy now available. It doesn't have to all be man or animal based, and we don't have to get next to a river or stream. I can generate power to make my goods anywhere that I can get fuel to. Right? So a lot of interesting things happen in this time period in the 1700s, and that allows us to become more and more specialized beyond that. In the 1800s, we begin seeing the steam engine applied to vehicles. The telegraph occurs during this time frame, and somebody realizes that if you generate a spark on one end of a wire pair, that spark can also be sensed or felt or even heard on the other end of the wire. And we're literally at this point communicating at the speed of light. Right? So instead of having to get a message to Oregon from Kansas City, you have riders on the Pony Express riding the horse just as hard and fast. It'll go one right after the other. 2-3 weeks to get a letter from Kansas City to Oregon. Now it's just as fast as you can put a wire up and tap on the other end of that wire. Okay. 20th century. So the iron horse, some of the earliest versions of the motorcycle is kind of in the late 1800s. Around the late 1800s, the first actual, what we would consider an internal combustion engine, a gasoline-powered engine, begins to emerge in the late 1800s. And basically around the early 1900s, the 20th century, we start to see what resembles a modern automobile for us. Okay? So think about that. So from the early 1900s until, when did we land on the moon? 1969. Less than 100 years, less than 70 years. Roughly about 70 years from the time frame where we don't even have cars to putting a man on the moon. Why? These 4 things. We no longer have slow communication of ideas. Telegraph, soon after the phone lines, telephone, and then we continue from there. The internet existed in its infancy between large research institutions. There was the ARPANET in the 50s or 60s, I believe. Okay, fear of technology being used against you. So we get into the late 60s and 70s. We've already gone through the world wars, and we've recognized as a global society that we've got to try to get better at that, and we try really hard, and I think we've done some good things there. But again, standardized methods, the metric system has existed by the time we get to the 1900s, the metric systems existed for centuries, a couple centuries at that point. So most of the world's talking the same language. We're still trying to figure that out. Other day-to-day tasks, you've already got a lot of the mechanized agriculture. That's already kind of occurred. So again, why does that happen so fast? Well, again, you've really done what you can to mitigate or destroy those 4 factors that slow us down. Okay? All right. So where are we at? Well, majority of the population in the world if you have the technology, you can have access to the internet as long as you can get a view of the southern or northern sky, depending on what hemisphere you live in. Now, do you have the technology? That's another question, but there are just about the entire globe is connected to the internet, or at least you could get to somewhere that is. You have supercomputers capable of over quadrillion calculations per second. That's what we call flops. That's addition or subtraction of decimal place values. Okay, quadrillion times per second. The largest computers are capable of doing that. I don't know what these, what these guys clock the computers in the room here. I don't know what they clock in on. I'm not an expert there. And think about GPS, right? Think about if you go somewhere else today. I mean, it was not that long ago that you had to ask for directions or know kind of how to get around, or you stop somewhere and how do I find this place? Now you just ask your device and it tells you how to get there. And they've gotten pretty good at that. That's crazy. Right? And now we're approaching the point where the cars we're basically there, where the car is going to take you there itself. Part of that's because we have computers capable in smaller packages capable of doing more. And that's, you've got another aspect here of engineering. You guys kind of hit on this, using things to do other things. Yeah, that's definitely part of engineering. Think of all the places where you see a round rotating object doing something, right? That's a wheel. So you got 3D printers, you got hard drives. I mean, it's just simple things off the top of my head there. Arguably the nuclear reaction was initially designed to harness for energy, but it was very quickly, because of the situation and the time frame, it was very quickly spun into weapons. But another one that's probably the best example is the idea of a transistor. Sometimes you can talk to your grandparents, they might talk about a transistor radio, and the idea, now, I'm not an electrical engineer, I'm not an expert here, but roughly my understanding of a transistor is it's basically like a valve for electricity. Think about it like a valve for electricity. So and the most simple transistor is going to have 3 leads. You're going to have basically an input, an output, and a signal. And what you can do is you can control how much electricity goes from the input to the output based on how much signal you send in the third leg. And so the idea of your transistor radios, they were using this transistor along with other circuitry that we're not going to go into here to basically take this large carrier signal that was easy to broadcast through the air and embed within that a much smaller audio signal, and using this valve to kind of control how much of that carrier signal does or doesn't get through, you can strip out the audio signal within and then amplify that up to be heard. Really butchered that description, but that's kind of a nice simple description there. Most transistors that are built today are not used in this fashion. So think about if you've got like a water hydrant, you can kind of use that as a switch, right? You can turn it completely on, or you can turn it completely off, right? On, off, 1, 0, 1, 0, 1, 0. This is binary. Most transistors we build today, we basically use as switches. They're either on, that's 1, or they're off, that's 0. And that's what we use them in. Right? So they're approaching the point where they're talking about transistors. They think they've got them down to where we're hitting the molecular limit as to how many molecules is required to build a functioning transistor. And that knowledge, researchers have generated that knowledge, we believe. And so now we've got to figure out how to make practical use of it. Okay? So if you can get a transistor down where it's tiny, and that's what we've spent the last 2 decades, getting transistors down to where they're tiny, and we can put more and more into a small device, and now you've got your cell phone. Didn't even show up here, right? Because we take that for granted. Okay? Now you've got this mobile computer that has more abilities than what they had on the first moon lander. Okay? And you just carry around in your pocket. You don't even think about it. Right? That's because we've been able to get transistors smaller and smaller. So we've got these lots and lots of on-off switches that control the flow of electricity that we can use then to do lots and lots of calculations very quickly. without a lot of electricity or a lot of energy. Okay. So that's a little bit about history of engineering, innovations, where have we gone, how do we get there. There are various fields of engineering, and later on in the semester I'm going to talk about these fields of engineering, but I'm not going to talk about them today because I'm going to ask you to go out and learn about them first. Okay, and that's so various fields of engineering. This is not a complete list. In fact, there's a second page. Here's another smaller list. There's all these fields of engineering. Of course, this is out on Canvas. Go look or find one that you're interested in. Now, why am I mentioning these? Well, because I've got 2 assignments I want to introduce to you today. Okay, now this stuff's out there in Canvas. Assignment 2, again, get assignment 1, that information file done and sent to me. Assignment 2, these 2, I'm going to show you 2 different assignments here, and they both have due dates. Okay, now I'll take them after the due date, but if you want full credit, get them to me on the due date. So when you go to Canvas, you go to assignments, you can go to, I'm just going to load this up. All right, so I've just loaded a Word file. You can download that and look at it, or you can just look at the preview here. Okay, in Canvas, I think you can pull this up on your phone too. You only have to go to a computer. We'll go to full screen mode here, and let's zoom in. And go away, thank you. Assignment 2, the innovation paper. Okay, this is a simple research paper assignment. Give you an opportunity to receive some feedback about your writing prior to the larger research paper assignment. We're going to talk about the fields of engineering paper here in just a second. There is a list of innovations I placed in Canvas for you. All right, it's right there. It's in the assignment 2 folder. I'll show it to you in a second. What I've done is I've scanned the inside cover of this text, Engineering Your Future. And this PDF in there has got a list of innovations we can look at in just a second of things that have occurred in the last couple of millennia. I want you to choose one that interests you, and I want you to learn a little bit about it. All right, so go learn something new. Conduct some basic research. I don't mind you using internet resources. I don't even care if you use Wikipedia. Just don't make that your only source. Don't make any internet source your only source, right? Come on, guys. This is any idiot can put up a website. Use reputable sources, but always check at least more than one source. If you get conflicting information, go to another source and see what you can find. Try to find a more better funded source that's got more people doing research. At any rate, pick a topic, learn a little bit about it, and then write a short research paper about it. Talk about the importance of the innovation. Okay, talk about when or about what time frame did it occur, what led to it, and then talk about the people or individuals that came up with the innovation. What made them tick? Why in the world did they decide to do this crazy thing that nobody else had done before? Okay, or at least nobody had done successfully before. At least a page of text. You're going to have a works cited page also, so there's going to be at least a page of text and a works cited page. Okay, if you do these 3 things and take them seriously, you shouldn't have any problem getting at least 3/4 of a page of text, especially when you can do double space. If you double space, that gives me room in between your sentences to write things. Okay, make comments and whatnot. 12-point, either Times New Roman or Calibri is fine. Don't use 12-point Arial, that's just too big. Let's see here. Use proper citation techniques. Whatever they're teaching you in your composition class to do in-text citations would be just fine. If you have no idea what I'm talking about, come talk to me. Let's talk about it. Looks like most of you guys are either taking composition or you've already taken your composition classes, so do some parenthetical documentation, right? So you're going to learn about something new that you didn't know about. Tell me where your knowledge came from, okay? And have at least 2 sources, and you're going to have to specify, all right, well, this information came from this source, this information came from that source. I don't really want you to put quotes in your book, in your report. That's not actually what I want you to do. What I want you to really do is I want you to go out and get some existing knowledge and put it together in a practical format. That's what I'm asking you to do. Does that make sense? I'm not asking you to copy paste stuff off the internet. I know you can do that. I'm not worried about that. If there's something that you just really want to put a quote in your report, just do it correctly and that's fine. But again, parenthetical documentation, citations, in-text citation. If you don't know what I'm saying, come talk to me, or let's get you to the writing lab. Let's make sure we get you caught up on that knowledge. Okay, it's easy to do, but we need to make sure you know what that is. Utilize that within your text. You're gonna have research information from at least a couple of sources. Just make it clear which source was used where. You don't have to put a citation after every sentence. If a whole group of sentences came from the same source, just put it at the last sentence where that information come from. Okay? All right. Again, if I'm talking Greek, please come talk to me. Let's make sure we get you on the right page. And again, I said there's no reason to include large blocks of quotations from other sources. I really want you to paraphrase. Don't plagiarize. You can quote if you do it correctly, but there's no reason to. I'm really interested in your ability to take in new knowledge and do something with it. Okay. This one's due next week. That way, it's I get it back. It's real short. Shouldn't take you too long. I get that back to me. I turn around and I can get it graded back to you, and you get some feedback. Hey, here's you need to do parenthetical documentation here, not there, and we go from there. But again, page of text, a works cited page, at least 2 sources. Use MLA, APA format, whatever you're comfortable with. Some sort of in-text citations. Have that into Canvas in a PDF or a Word document by the end of the day next Thursday, a week from today. The innovation list, again, right here underneath it in Canvas, right? And so this is just a scan from a textbook. It's a little rough, but you should be able to read it. Right? If you can't read it, you might download it from Canvas and then open it up in your PDF viewer on your device. Okay. This preview here looks a little crappy, but you can probably download it and get a better view. But anyway, so they're saying for several millennia, they're starting at 1200 BC to 180. They're listing a few things, and you go to the next page, and they're saying, all right, well, from over the next 1,000 years, here's some things that happened, and then over the next 400 years, here's some things that happened, and the next 300 years, here's some things, and notice the list gets longer. All right, so over the next 300 years, here's a bunch of things that happened, and then PDF generator is going to give out on me and not show me the rest of it. It's, again, if you want to download this, let's just do that. Come on. Open. So yeah, so you download it, you're going to get a better view of it. All right. So 14 to 1700. So again, just go through here and pick something out of this list that interests you. Something that you don't know about. Go learn some new things about it. Okay? And then put together a simple one-page paper form. Okay? That's the first assignment. Let's talk about the other assignment. This one I call the Fields of Engineering paper because I'm going to ask you to go learn about 3 fields of engineering. Right? Pick out 3 fields, and the goal of this assignment is really for you to kind of take some time and learn a little bit about, a lot of people might show up here and say, well, I want to be a mechanical engineer. I want to be an electrical engineer. Okay, why? Do you know why? And maybe you already do. Maybe this will go pretty quick for you because you've already done this before. What is it about that field of engineering that you're interested in? And then what are some other fields kind of like it? Do you know the differences? Are you aware of the differences? It's not uncommon somebody will do this assignment. They'll come to me and say, hey, Steve, once I learned about industrial engineering, that's really kind of what I wanted to do anyway. I don't think I'm going to do mechanical now, or whatever the case may be. You actually learn about another field and realize that's actually what I wanted. And that's okay. And sometimes it just reaffirms, no, I am for sure going to be electrical. This other stuff doesn't interest me. that's fine too. Pick 3 fields of engineering, write a simple paper on that. Let's go back to Canvas here, and let's go look at that one. Okay, that's PDF. Here we go. All right, so we go back to the assignments folder, or the modules, and the fields of engineering papers here. This one's due September 17th, so basically you get 4 weeks to work on this one. Okay, you have 4 weeks to work on this one. I'll take it after that at a penalty. Same thing with the innovation paper. The innovation paper's due next Thursday. I'll take it after that at a penalty. Okay, so those are about the, aside from the final project, those are about the only 2 assignments I normally put due dates on, is these 2 here. All the others, last day to withdraw is the absolute cutoff. Same thing with these 2. You'll get them at a penalty if you turn them in after these dates, but I won't take them at all after the last day to withdraw. All right, 3 fields of engineering. Write a simple research paper about those 3 fields. I specify 4 to 5 pages. I've given A's to 3-page papers, and I've given F's to 7-page papers. I'm more interested in your content than I am your length. Okay, much more interested in the content than I am the length. Again, similar formats, Calibri, Times New Roman are fine, 12 point on those. If you use Arial, go a little smaller. Most of you are just gonna, I think both Word and Google open up in Calibri, 12 points, so just use that. Double space is fine. You will have a works cited page. I do expect in-text citations or parenthetical documentation, some kind of in-text citation. If you want to do a numbering system, I can live with that. Just be consistent. Again, due September 17th. That's 4 weeks from today. What do I want you to talk about? Well, again, pick 3 fields. Talk about the history of the field. How did it come to be? How did the field of civil engineering come to be, or whatever the case may be? Talk about the type or types of work that most people in this field do. If you talk about the work that every person in this field does, obviously this is not a 4 to 5 page paper. This is much longer. Just what are some of the most of the people in this area do? Give us kind of a brief description of that. Go look and see what kind of companies are hiring these types of engineers. Okay? And then go find a couple of universities that have ABET accredited programs where you can go study this particular type of engineering that you're interested in. I say the 2 closest. You could, if you know that you're not going to be here in this state after you're done with this class, or after you're done here at this school, you're going somewhere else, then just pick 2 schools that make sense for wherever it is you want to go. Okay, it doesn't have to be the 2 closest, but if you know you're going to be here after you're done here in this state, then pick 2 that are closest to us. Okay. So some of the fields like nuclear engineering, you're going to have to probably not, that doesn't exist in this state, or at least there's no programs for it, but there are some around the country. Okay, so again, just take an opportunity, look at and learn something about a couple of fields you didn't know about. All right, take this opportunity to figure out what this really is and if this is really what you want to do. Okay, again, don't copy paste information. Same thing on the innovation paper. I'm going to run it through a plagiarism filter. It's going to pick up real quick and say, oh no, this is from Britannica.com, and if you haven't properly quoted it, that's an easy F. Okay, if you properly quoted it, I'm still going to have a conversation about, I don't really want large blocks of quotations. I'm not interested in your ability to copy paste from the internet. Even if you do it correctly, that's not our goal. Our goal is for you to learn something new, gain some new existing knowledge, and put it together in a practical format. Okay? Funny how I keep going back to that. Questions, comments, complaints for me? They're all fair game. All right, guys. Let me take roll, and I'll turn you guys loose. Let you guys use your time as you like. Let me stop the video because I want this to be sanitized.